This is the solution to problem 6-36 of Halliday, Resnick, and Walker. So let's go look at the problem here. So this is talking about terminal speed. So it says terminal speed of a skydiver is 160 kilometers in spread eagle, and then it's faster, 310 kilometers per hour in the nosedive position. So now we're asked to find the effective cross-sectional area. So how are we going to sort of do that? Well, first let's sort of just make sure we got a picture of what's going on here. So here's our skydiver falling at speed v. And what do we know about forces that act on this person? Well, certainly there's going to be the force of gravity. That's always going to be there, acting on her, heading downwards. But then since she's traveling with the speed v, we also know there's going to be an air resistance force. So we can draw that guy in there, F air I call it. And we know that there's a relationship there that says that force is got some constants in front of it, and then it's proportional to the cross-sectional area, and then also the speed and the speed squared of the person who's falling. So the other thing we know then is that if you sort of jump out of an airplane, skydiving, that your speed will increase until you get to the point where the air resistance force here is just equal to the force of gravity. So it will increase a little bit as your speed increases until that force is equal to the force of gravity. So we can write that then as F air equal Fg, or you can sort of put in the equations here to say that terminal velocity v squared times the area times a bunch of constants is equal to mg. So that's sort of what's going on here. Now, we've got these two different cases. We've got the person in the spread eagle position the way we've drawn it now. So let's just relabel that, call the area the cross-sectional area. And in this case, the cross-sectional area is kind of, a circle there, I guess, for the skydiver. And then we'll call that, rather write terminal every time, I'll just call that V1. So that's the equation now that describes that particular scenario. Now, for the second case, the diver sort of turns to be headed face down, so we can go ahead and do that. So there she goes. And you'll notice a couple things happened here, maybe. The air resistance force gets smaller. So why is that? Well, it's because this cross-sectional area now is significantly smaller. Now that she's headed sort of nose down, it's a smaller effective cross-sectional area. So we can represent the fact that that air resistance force is smaller then, according to this equation. Notice that right now we've still got the same velocity, v1, that we had up here. But the area A2 is smaller, so that air resistance force has gotten smaller. But of course what happens now, the force of gravity is bigger than the air resistance force, so there's going to be acceleration. And what happens is the person, this skydiver, is going to increase speed, so we can watch that happen. The velocity increases, and at the same time the velocity is increasing, the air resistance force is increasing as well, and the velocity just increases until the force of gravity and the air resistance force are again equal to each other. So we can write that then for the second set, we reach a new velocity v2, and that corresponds to the area A2, but those are the air resistance force, and again, that's just equal to mg. So now we've got this relationship that the original sort of cross-sectional area and velocity combined to equal the gravitational force, and now we've got the new relationship here that says for the new cross-sectional area and the new velocity, those are also equal to mg. So it's pretty straightforward then. You can just set those two things equal to each other since they're both equal to mg. And now we've got various constants here, but we can divide all those out. We can get rid of the 1/2 and the c in the row because they show up in both equations. And so you can rewrite that just as a1 v1 squared is equal to a2 v2 squared. Then what we're interested in here is up here, the problem said find the ratio of the cross-sectional area of the slower position to the faster position. Well, remember, A1 and V1 were the slower, the velocity when the area A1 was bigger. So we can solve then for this ratio that we're looking for just by dividing A2 over here and divide the v1 over to here, and then I just put those into a single fraction and squared that. So now it's actually pretty convenient. We can just put in the two velocities. And notice we don't have to bother doing any conversion to meters per second, because if we converted the top number up here, we'd multiply by some constant conversion factor, and we do the same conversion factor down here. So in fact, we could just use kilometers per hour and not have to worry about doing any conversion. So when you put those numbers in and then square, because it depends on the velocity squared, you end up with 3.75, and that's the answer that Wiley Plus is looking for.